They're kind of the arteries of our modern world, right? Millions of miles of pipeline, mostly hidden right under our feet. But the engineering that keeps them from failing, well, that's a fascinating story of physics, materials, and one single critical calculation. Okay, let's get into it. So it really all boils down to one question. If you're an engineer designing one of these things, what's the one number you absolutely positively have to get right? I'm not talking about length or cost. It's something way more fundamental. Yeah, because getting that number wrong, it has catastrophic consequences. When a pipeline fails, it is devastating. So pretty much the entire field of pipeline design is focused on making sure this exact picture never ever happens. So, to understand how they prevent these failures, you first have to stop thinking of a pipeline as just some static tube. You gotta see it for what it really is, a structure that's fighting a constant, invisible battle. Think about it this way. A pipe isn't just sitting there. From the second it's put into service, it is an active structure, in a constant tug of war, resisting these incredible forces that are always trying to either rip it apart or crush it flat. And this slide just shows it perfectly. These are the two main opponents in that fight. On the inside, you've got all this pressure from the gas, or liquid, pushing out, trying to burst the pipe open. And at the exact same time, from the outside, you have the crushing weight of the earth and the water trying to squash it. Oh, and it doesn't stop there. Not even close. Engineers also have to worry about the stress from just building the thing. Or if it's offshore, a seabed that's constantly shifting. The pipe itself expands and contracts with heat and cold. And you even have to plan for things like a ship anchor accidentally hitting it. It's an incredibly hostile environment. So how on earth do engineers deal with all these forces? Well, they definitely don't leave it to chance. They have a very strict set of rules to follow. You could call it the official engineering rulebook. And this is absolutely key. Designing a pipeline isn't about having a good feeling or guessing. It's a super rigorous, disciplined process that's built on decades of research, hard-won experience, and tons of data. And it's all written down in these official codes. And this is one of the rulebooks. A standard like ASME B31.8 is basically the Bible for gas pipelines all over the world. It gives you the minimum requirements, the formulas, the safety rules, everything that a design has to follow. No exceptions. Okay, so the code gives you the rules of the game. Now, within those rules, engineers have two primary weapons to fight that battle of pressures: the steel they choose, and just how thick they make the pipe. This is their armor. And right here, this brings us to the absolute heart of it all. According to our sources, this is the single most important decision an engineer has to make. Pretty much everything else depends on getting that wall thickness exactly right. So here's the fundamental trade-off laid out plain and simple. The problem is the immense pressure trying to burst out. The solution? Well, you have two knobs you can turn: how strong your steel is and how thick you make the wall of the pipe. Let's talk about the steel for a second. Its most important property is something called minimum yield strength. Okay, so as you pull on a piece of steel, it stretches, but it'll spring back. The yield strength, that's the point marked sigma y right there, is the point of no return. It's where the steel stops springing back and just starts to stretch permanently. You never, ever want to reach that point. And this isn't just some abstract idea. Engineers literally choose from a menu of standard steel grades, like you see in this table. An X52 steel, for instance, is guaranteed by the manufacturer to have a minimum yield strength of 52,000 pounds per square inch. This known strength is the first big piece of our puzzle. All right, so we've got the pressure pushing out. We've got the known strength of the steel pushing back. Now, we need to connect those two things with the master equation that is at the very core of all pipeline design. The concept that connects everything, the key that unlocks the whole problem, is something called hoop stress. That's the technical term for the force inside the pipe's wall that's fighting back against that internal pressure. And this diagram shows it perfectly. As the pressure inside pushes out, it creates this stress that goes around the circumference of the pipe, like a hoop. Honestly, the easiest way to picture it is to think about the skin of a balloon as you blow it up. That tension you feel, that's hoop stress. So how do you calculate it? Well, you use a beautifully simple but incredibly powerful equation called Barlow's formula. This is the foundational calculation that those design codes we talked about tell engineers to use. And here it is. Don't let the letters fool you. Its power is in its simplicity. The hoop stress, that's sigma h, equals the pressure times the diameter divided by 2 times the wall thickness. See how it works? If the pressure goes up, the stress on the pipe goes up. But if you make the wall thicker, the stress goes down. This is the balancing act that every single pipeline engineer has to master.
But hang on, there's one last crucial piece to this puzzle. The physics are the same everywhere, but the risk definitely is not. The final step is to take this universal formula and adapt it for the real world. And that all depends on one thing: location. Look, that raw calculation tells you how much stress the pipe is under. What it doesn't tell you is how big of a safety buffer you need. A pipeline failing in the middle of a desert is bad, but one failing in a crowded city is a whole different level of disaster, so the design has to account for that. And this is exactly how they do it. They bring in something called a design factor, which is that letter F in the equation. The rule becomes the hoop stress in your pipe has to be less than the steel's yield strength multiplied by that factor. Basically, this F factor acts like a mandatory safety margin, making sure the real-world stress is always just a fraction of what the pipe could theoretically take.
And this table right here is where it all comes together. This is from the code. Look at a Class 1 location. We're talking farmland, desert. The design factor is 0.72. That means you're allowed to design the pipe so it stresses up to 72% of the steel's total yield strength. But now look at a Class 4 location, a dense city with tall buildings. The factor plummets to 0.40. You're only allowed to use 40% of the steel strength. For the exact same pressure, this forces the engineer to use a much, much thicker pipe, building in a huge safety margin exactly where it matters most.
So in the end, that's the secret. The whole hidden science of keeping pipelines safe comes down to understanding that constant battle of forces, picking the right armor for the job, and then applying one elegant formula. But all of that is governed by a final, common sense rule: how close are people to it? It's really a perfect example of how fundamental physics gets engineered into life-saving safety.